So when we talk about the benzene, it is an overlap of 6 pi bonds. How does a pi bond look like? Think for a moment, it is a pi bond a million times, more than a million times magnified. It has 2 lobes. What are these lobes? These are nothing but electron clouds in the form of a wave function. There is a nodal point where there is no electron cloud. These have a little differentiation that they are one to each other out of phase. If I take the real molecular model of the benzene, that is like this. You see, these are the 6 pi bonds above and below. They are totally delocalized, overlap with each other. This is how exactly benzene looks like. It cannot be shown or demonstrated while we are talking about the UV, a model like this. So a framework model is shown. These are the two, this is above the plane, this is below the plane. You think this is the blue, you think this is the red. These are not actually rod-like, they are balloon-like, as I've shown. These are this, that they have an overlap. They overlap, they overlap, they overlap. Similarly, they overlap. And we get a model like this. This is the benzene shape. Then what happens when it is subjected to UV radiation? UV radiation, each pi bond is associated with certain energies. There are 3 modes of absorption. That is, one is the E bond, that is ethylenic. It has E, K and B. E is ethylenic, K is conjugated, B is a benzoate. What is E? That is the total from bonding. It is an overlap like this. When it is radiated at a frequency which is about 182 to 184 nanometers, they change one electron at a bond, changes the phase. They become from bonding to anti-bonding, like this I have shown. Alternate. This is bonding to anti-bonding. Previously all blacks were above, all whites were below. Now they are alternating with each other. That is, none of the pi bonds will overlap with each other, because white cannot overlap with the black or black cannot overlap with white. So when this situation comes, you can say this is anti-bonding stage or the E band. This is a transition with a very high energy.
Tests of significance. Tests of significance are the statistical tests used to find out whether the observed result is significant or not. So these are statistical tests essentially. For example, if a chemical reaction is carried out at 2 different temperatures like 40 degrees centigrade and 60 degrees centigrade, and the chemical reaction at these 2 temperatures is carried out at each temperature, say for example 6 times, and so you will get the 6 yields like Y1, Y2, Y3, Y4, Y5, Y6. These are the 6 yields in the 6 experiments carried out at 40 degrees. I will designate them as 140, this is also 40, just to indicate the temperature at which this yield is observed. Suppose you have taken a coin and when tossed 5 times, surprisingly you got all the 5 times head. That means a rare event which normally do not occur has occurred in our experiment, which means that you cannot reject your data, because by conducting an experiment you observed, got the data observed, and basing upon the observed data, now you have every reason to believe and to suspect that the coin may be wrong, coin may be biased, then only you will get such a result. Suppose what is meant by making the coin biased is, suppose if the coin is one surface is coated, is coated, say for example tail surface is coated with a magnetic material, so whenever you toss, head will come up. The surface that is coated with a magnetic material will go down, and the other surface, that means head, will always appear top, and hence the result is changed, bias is introduced.
Greetings to one and all. Welcome to this session on Parkinson's disease. Basal ganglia, as you all know, are a group of subcortical neurons which are present at the base of the forebrain. This basal ganglia consists of the cortex, the thalamus, as well as the brainstem. Here I have a diagram regarding which shows all the different regions of the brain which are involved in this movement disorder. What are they? We have here the motor cortex, the striatum, the thalamus, substantia nigra, globus pallidus, as well as the subthalamic nucleus. All these work together and there is a complex mechanism which is involved in the movement disorders what we are seeing. Here, SN stands for substantia nigra. Substantia nigra, as you all know, is again divided into pars compacta and pars reticulata. The term substantia nigra arose because of a substance which is present, that is neuromelanin. Substantia nigra means a black substance.
Greetings and welcome to this session on bioethics or clinical trial ethics. So bioethics or medical ethics or clinical trial ethics, depending on the context in which we're going to call it, is pretty much the same thing. It places emphasis on value of our actions. CIOM guidelines also talked about research in vulnerable populations. Vulnerable populations or special populations are children, pregnant women, elderly, prisoners, those who are mentally ill or not cognitively able to make decisions for themselves. So these people are captive populations where they're really not able to make those kinds of decisions for themselves. Children may be included in a clinical trial with consent, with parental consent, if you are trying to figure out a pediatric dosage or if you're trying to figure out a pediatric medication. There's absolutely no reason otherwise for children to be involved in clinical trials.
We know that nephrons are the basic unit of kidney. And when we say that kidney is injured or affected, that means the nephron is injured. So here a chart is given which clearly indicates with the picture of the nephron which are all the areas, which type of drugs and what is the mechanism of the kidney damage. For example, the acute tubular necrosis, it happens in the glomerulus because of aminoglycosides, amphotericin, cisplatin, NSAIDs, and when we use radio contrast dyes. So these are the drugs which can cause acute tubular necrosis. The drugs which acts on the PCT, proximal converter tubule, and causes myoglobinuria. For example, statins, methyl-dopa, dapsone, and quinines. These are the drugs which acts on the proximal converter tubule and causes myoglobinuria, that is release of myoglobin from the myocytes. The drugs which cause crystalluria also affects this proximal converter tubule. The drugs which cause crystalluria include methotrexate, sulfonamides, and quinolones. This clearly gives a picture that what are the drugs and what are the mechanisms by which it affects a nephron, which is the basic unit of kidney.
This is the structure of erythromycin A. In erythromycins, we see the general characteristics of this class. So this is the lactone ring made up of 14 atoms. Note that we have also counted the oxygen as part of the ring. We have also said that the lactone ring may contain a ketone group. You can see that at the 9th position. The lactone ring also contains two sugars. The sugar at the 5th position is a basic sugar and it is disosamine with the D stereochemistry at the 5th position. The sugar glycosidically linked at the 3rd position is a neutral sugar and that is cladinose. The stereochemistry at the 5' position is L. What happens to erythromycin when it is exposed to an acidic medium, for example, like the acid in the stomach? The reaction occurs between the 6-hydroxy group and the 9-carbonyl function. Okay. So in the presence of an acid, the 9-carbonyl group gets protonated and the 6-hydroxy group does a nucleophilic attack on the 9-carbonyl group which is protonated. So this leads to a ketal. Recall what is a ketal. If I have a carbonyl group and I reacted with an alcohol, then this is called a hemiketal. The carbonyl at the 9th position has now become bonded to the hydroxy group at the 6th position and also to the hydroxy group at the 12th position out here. So this is your ketal that is formed by attack of the hydroxy groups at the 6th and the 12th position on the carbonyl at the 9th position out here.
Let us look at how glucose is systematically broken down to pyruvate. There is one reaction which is significantly positive. In other words, in case of this reaction, the tendency to go from here to here is minimal. The reaction actually is favored in the opposite direction, where dihydroxyacetone phosphate and glyceraldehyde 3-phosphate might come together to give you fructose 1,6-bisphosphate. Reactions which have a very significant negative delta G prime values tend to be irreversible in the direction of conversion of glucose to pyruvate. It might appear that this reaction would be irreversible in the opposite direction. If this is so, then once glucose is converted to fructose 1,6-bisphosphate, there would be no tendency for glycolysis to proceed further in order to generate pyruvate. The mystery can be solved or understood by realizing that there is a difference between what is called as the delta G for a reaction and the standard free energy or delta G0 prime for a reaction. Although delta G prime or standard transformed values give you a feel for what is the direction or the thermodynamics of the reaction, in reality it is actually the delta G which dictates in which direction the reaction will go. Although delta G transformed values indicate that this reaction is going to proceed in this direction, while this reaction is irreversible in this direction, in reality what is observed is that the actual delta G values are actually fairly close to 0. In other words, these reactions are actually freely reversible in the cell. So rather than looking at them as irreversible reactions, one can look at these reactions as being freely reversible.
When we are speaking about temperature control, there are two methods of elution in the case of gas chromatography. This is how programming can be done today, because you have control over the temperature and you can vary the temperature at different periods of time. That means we have made the same 40 minutes of our chromatogram in a different manner, so that initially first to 10 minutes, 0 to 10 minutes, maybe we are getting a compound out of the column at 160. This is 160 degrees. 10 to 25 minutes up to this, probably we are getting a couple of components. Up to this, it is 200, and over that, we have risen to one more, that is 250 degrees centigrade. That is how you can vary the temperature by giving such commands in software that is running or that is operating the gas chromatographic equipment. So you can program a temperature so that the proper resolution is taking place. If probably we can show some examples where if it is isothermal, what is the type of resolution? If it is programmed, what is the type of resolution that we can get? We can show that there are several experiments demonstrated the advantage of programmed elution, programmed temperature, or programming of the chromatogram with variable temperature.